Hello everyone. In the last video, we have seen how to construct DC motor using transfer function, and we have simulated the DC motor in open loop. To see how to construct the DC motor using transfer function, see the description where the link is given. Now we are going to see how to control the speed of the DC motor using a PID controller. That is, we are going to see closed loop simulation of the DC motor. For that, we need to take the speed feedback, and then we need to give the feedback to a comparator where the reference speed is given, and we need to use a controller, PID controller, to control the speed. Let us take the speed feedback. The reference speed is given as 100 RPM. So we need to take the speed in RPM, actual speed in RPM, and we need to give the feedback. And from the controller, the output of the controller will be given as the input to the DC motor. So we need to remove this constant DC voltage, because to change the speed or to control the speed in closed loop, we should not give constant input voltage. The input voltage should be varied to achieve the desired speed. That is, this method, we call it as armature voltage control. So we need to change the armature circuit voltage in order to change the speed. So we will be giving the speed reference, which is 100 RPM. For that, let us take a constant block. So this speed will be initially taken, that is, the reference speed is taken as 100 RPM. This 100 RPM should be given to a summing point. Reference speed is given to a summing point. The actual speed should be given to the minus sign of the summing point. So this is the speed feedback, which is given with a negative feedback, and the output of this will be given to a PID control. So the reference speed minus the actual speed, which is the error speed, is given to the PID controller, whose output is directly given to the armature circuit. The output of the PID controller is now given as the input to the armature circuit. Now we can click on this, double click on this PID controller to see the values of P, I, and D. The default values of Pi are 1 and 1, and derivative is 0, and filter coefficient, it is given as 100. These are all the default values. We can run this circuit, we can run this model with the default value and check whether we are able to get the desired speed. Now it is running. So the desired speed, it is obtained as 99.4 RPM. We can check the speed curve. Since with this we cannot, the steady state is not reached, so we can run this model for around 60. We can change the stop time to 60, and again we will run, and we will also give the reference speed as one of the inputs to this scope to see how the actual speed is coming with respect to the reference speed. Now we can run this. So this is the speed curve. The blue line shows the reference speed, and this yellow line is the obtained speed. Now you can see that in the display it is coming as 100. So we will be able to get the desired speed of 100 RPM with the default values of Kp, Ki, and Kd. But we see the speed response. We could notice that we have more overshoot, peak overshoot, and then it reaches the desired speed after around 20 seconds. So we need to change the values of Kp, Ki, and Kd in order to suppress the overshoot and also to reduce the settling time. For that, we can click on this PID controller. And in the PID controller, we have an option called tune. If we tune that one, the values of Kp, Ki, and Kd will be tuned according to the parameters of the motor. So we have this option in the MATLAB if we use the system with the transfer function model. So with the transfer function model, if we click on the tune, the MATLAB will auto-tune the Kp, Ki, and Kd values, that is gains of the proportional, integral, and different derivative controllers, and it will give us the tuned values of the gains. Now, still it is tuning. Once the tuning is completed, we will get the output, the response, with the designed value of designed value of the Kp, Ki, and Kd, and the actual values of without a design. What is the response? So the dash line shows our actual response without tuning the Kp, Ki, and Kd. And if after tuning, we are getting this value of we are getting the blue line. The continuous line shows the response for the tuned values of Kp, Ki, and Kd. The tuned values are listed here. So we can notice the values of Kp, Ki, and Kd here. The Kp value is 0.8871. Ki, that is the gain of the integral controller, is 0.4969, and the differential gain is 0.354. So this is the values of Kp, Ki, and Kd, and the n is it is tuned as 97.77. So with this value, if we simulate, then we will be able to get the response as given by this continuous line. And the settling time is also it is now reduced to 18. But at 18 seconds itself, we will be able to get the steady state operation. Now we can even adjust the response by changing the. So we can find out the tuned response at different points, and we can even tune the response by adjusting the response time. So if we can have the slower or faster response, and then again we can have this aggressive transient behavior. This one also we can adjust this to change the transient behavior. So like this, we can, if we adjust this, we will change the response value, and for that response, what should be our Kp, Ki, and Ka value we can have. I'll just copy the parameters to the model in order to change the values of Kp, Ki, and Kd. So we got the P value as 2.459, and I value we got it as 1.315, and T value we are getting it as 1.094, and the filter coefficient N we are getting it as 213.9. So with this value, if we simulate, we will be able to get the response as we got in the tuning window. So this is how we are getting the response. Since the settling time is lesser, we can reduce the stop time to even 30 or even 20 also. So this is the yellow waveform shows the actual wave speed, and the blue line shows the reference speed. So with the tuned values of P, I, and D, we could get the perfect closed loop control. And we can even change the reference speed and check whether we are able to get the changed set value of the speed. So again, even if we change the reference speed, we are able to get the speed to the set value. And instead of changing the speed every time in the constant, we can have a slider block, and we can link this slider block with the constant, this constant block. So here you have, if you double click on the slider block, you will get here connect. We need to click this constant block, and then we have to tick that one. So with this, if we do, we can even change the name of the block, constant block, as a reference speed. So we will have this slider value here. So if we change the slider value, we will be getting the constant value as set by the slider value. So we can see the value of the constant block, which is changing with respect to the slider. If we move the slider, we will be able to change the reference speed value. Okay, now we can run the simulation. Let me run the simulation for around 100 seconds. Or let me run this for 50. So the set value of the speed is 50.46, and we are able to get the speed as 50.46. And now we can see the graph here. So again, we could see that we are able to get the speed as equal to the reference speed. So likewise, we can change the value of the reference speed by just sliding the contact of the slider block. So if we do that, we'll be able to change the reference speed, and we can check the closed loop simulation. So this is how we are getting the reference speed. We are getting the actual speed, which is following the reference speed. So in this video, we have seen the closed loop simulation of the DC motor, which is constructed with the transfer function model. And then we have also seen the closed loop simulation with the PID controller, and how to tune the PID controller. The tuning of PID controller, it is done in the MATLAB window. And with that tuned values, we have seen that the actual speed is the PID controller is able to control the speed, or it is able to control the speed to the reference value of the set speed. And we could also adjust the time domain specifications. So this is how we can control the DC motor in the closed loop. Thank you.